Now, this has led to yet another attitude, and some of which, if you were listening to the discussion last night, was even expressed near the end of the discussion last night. Maybe we should just accept the story. Maybe we should lower expectations and just accept the fact there's a multiverse and we happen to live one part of it. Let's not, maybe we're wrong to try to explain why we're likely. Maybe that's just wrong-headed. We should just be happy that we have a theory where everything we observe could possibly exist. What about that idea? Well, I have my own view on that. No, I'm sorry. We live in an extraordinarily simple universe with very special properties. Special properties on the macrophysical scale where our universe is extraordinarily uniform. It has this beautiful scale-invariant spectrum of hot spots and cold spots. On the microphysical scale, we heard from Maria this morning that the physics that underlies and from Robert, the physics that underlies our universe is in some sense extraordinarily simple, can be reduced to extraordinarily simple forms. Are we really, in order to explain this very simple universe that we observe in, are we really going to imagine that it's really part of a multiverse in which all these other complicated things are going around but that you can never ever test or see? Do we really need all that stuff in order to explain this one simple universe? I say no. I say we have to look for a better idea. We have to look for an idea which avoids this kind of breakdown, this kind of eternal multiverse idea. I would say it's, since we're talking about rethinking science in this meeting of World Science Festival, it's time to rethink this story. So, what do you do as a theorist when you rethink? Well, you go back and you ask yourself, well, what assumptions did I make that got me to the present mess I'm in? And what can I change to fix things? So, what assumptions did we make? Well, we thought about the idea that the universe has a Big Bang as a beginning. Out of the Big Bang, there's some quantum mess. We don't know what it is. And then we needed something to fix it up. That's why we introduced inflation. But once we introduce inflation, we end up with a multiverse. And okay, so we got to go back and we got to change something. Well, what might we change? Well, one thing you might change is this notion that coming out of the Big Bang came something random and unpredictable. Maybe the Big Bang is some process, when we understand it properly, that produces the very simple universe we observe. Maybe when we understand quantum gravity, for example, maybe from quantum string theory, maybe when we understand it properly and how it works, we'll discover actually where you end up with is a flat, smooth universe with tiny ripples and hot spots and cold spots, which are scale invariant, which the distribution is the same from scale to scale. It's not inconceivable to me. I don't know how to do it. I don't think we're there at this point. I'm going to keep my eye open for that, but I don't rule it out. What's the other thing we could do? Change. Well, how about this idea that the Big Bang is the beginning of space and time? That was never a proven idea. Even the fathers of Big Bang theory, people like Friedman and Lemaitre, they didn't believe that the Big Bang was the beginning of space and time. When Friedman wrote down his models, his solutions to Einstein's equations, he actually had the idea that the Big Bang, what we call the Big Bang today, was really a big bounce. And so what about that idea? What if we replaced the idea that the Big Bang, instead of having a Big Bang, we had a big bounce? That the Big Bang was really a transition from a state of contraction into a state of expansion, which I'm trying to illustrate in that diagram there. This is an idea that several of us have been pursuing as an alternative to the Big Bang inflationary picture. And let's see how far we've gotten with this story. So in this picture, as I'm trying to draw it, the universe, as I said, undergoes a phase of contraction, bounce, and then expansion. Now, of course, once you begin to think about this idea of a bounce, the Big Bang being a bounce, and that you can rebound from it, it's almost inevitable you might think about this bounce happening more than once. So it might have happened many times in the past, bounce, expansion, contraction, and it might happen in our future. So a particular version of these bouncing cosmology, which I want to focus on today, is a cyclical version of it, in which, at least approximately, these bounces occur at regular intervals. Imagine them occurring, let's say, once every trillion years or so, just to get your mind into the game. Okay? Each bounce, new matter and radiation will be created, which will create the seeds for the next round of galaxies and stars and planets and the like. The universe would then enter a phase in which dark energy would take over the universe. This dark energy would cause the expansion of the universe to accelerate, just as we're observing. But this dark energy would not be stable. It would eventually keel over into a negative form of energy, which would cause the universe to contract. Now, Max talked about things ending in a big crunch and just ending there, but there's no reason, as I said, that we know of that it has to be the end of the story. Instead of the big crunch, it could be a big crunch, big bang. That is to say, a bounce. And then the process would begin again. That's sort of the conceptual framework of the cyclical picture. So there's no inflation here that's going to be driving the story. It's going to be something else that's going to explain the cosmological properties we observe. So, why consider a bounce? Well, first of all, the moment you begin to think about a bounce and think about this phase of contraction, you discover there's a simple solution to the flatness and the causal horizon problem, which don't require any inflation at all. The contraction does it for you all by, the period of contraction does it for you all by itself. How is that? Well, let's first of all think about the causal horizon problem. So I'm talking about the fact, as Max described, that we had this puzzle in the original Big Bang picture. Then we looked at distant regions of the universe and opposite sides of the universe. They are very, very similar properties, very similar temperature to 4 or 5 decimal places, even though in the original picture there was not time for since the Big Bang for them to exchange light or forces or interactions or any other information. But that relied on the idea that the Big Bang was the beginning of time. It depended upon that idea. That's what started the clock. If I now say the Big Bang is a bounce, I now have all that time before the bounce for those regions to have come into interaction. There's no problem if you give me more time to get the two to interact. So the causal connectedness part of the problem, the fact that they're causally connected, have to be causally connected in the past, happens automatically in a universe which has a period of contraction before the bounce, if we change the bang into a bounce. Now, what about the flatness problem? That's a little bit more subtle. I'll try to argue it without showing an equation, although it's pretty simple to do with equations, too. I'll just try to do it by logical analysis, by thinking, first of all, about the original flatness problem of the standard Big Bang model. So in the standard Big Bang model, the idea was we had a bang, and the universe was filled with the matter and radiation that resisted the expansion of the universe, causing its expansion to decelerate. In a decelerating universe, what we learned is that if we had a tiny little bit of curvature or warp in the universe at the beginning, it would grow more and more important as the universe evolved, eventually taking over the expansion of the universe. And so when we looked at the universe today, it should be so curved after this long period of slowing expansion. It should be so curved that it should be obvious when we look at the universe. It should be obvious, for example, when we follow the paths of light from distant stars through the universe. But we don't see that effect. We see that the universe looks flat or Euclidean, and inflation was designed to explain that. It was introduced after the bang to explain that. But instead, let me have you consider another possibility. Take the picture I just explained of a slowing universe in which the curvature is becoming more and more apparent and run it backwards. You can begin with a region which has a large curvature and it's contracting slowly, and as it contracts slowly, it would become flatter and flatter. So just reversing the process of the Big Bang, having contraction rather than expansion, instead of making the curvature grow, you instead have the curvature decrease. So by the time you reach the bounce, the universe is already flat automatically. Now, after the bounce, the universe is expanding again, so the curvature is beginning to grow again. But there's only been 13.8 billion years for it to grow. So long as you had enough contraction before the bounce to make it flat enough, then the 13.8 billion years since is not enough to curve it again, to give it any significant curvature. Actually, that's no different than inflation. See, inflation doesn't really set the curvature to 0. It flattens it a lot during a brief period of inflation, and then there hasn't been enough time since inflation for that curvature to grow back again. We're using the same idea, but instead of inflation, contraction can do the same thing. So without introducing an inflaton, without introducing any potentials or anything like that, just having the universe going to go a long enough period of contraction, you automatically solve those two problems. So that's interesting. That's a good start. Now, but you want more than that. You actually want to make sure the universe is isotropic, looks the same in all directions. You also want to make sure that you have these fluctuations that are going to end up forming the hot spots and cold spots in the microwave background and forming the seeds for galaxies and all that. So where's that going to come from? Well, for that you end up having to do, at least as we presently understand it, you end up introducing elements that look a little bit like inflation, scalar fields with some sort of energy curves, there's different kinds of energy curves. When you introduce those, though, it turns out, if you introduce the dark energy, introduce those, you end up with a period in which the universe undergoes a period of a cycle ago of dark energy domination, just like we have today, then that dark energy decaying into a form of energy that causes this slow contraction in just such a way as to keep the universe smooth and isotropic. So, for example, the dark energy that's occupying the universe today will, over the next trillion years, spread out and smooth out the distribution of matter in the universe. And if it begins to decay and start slow contraction, we'll enter that slow contraction phase in what is already a smooth and flat universe. And then the slow contraction plays the role of keeping it that way, keeping it smooth and flat all the way to the bounce. But not perfectly so, because there's always those quantum fluctuations that prevent you from keeping the universe perfectly uniform. So while you're contracting, it's not true that every part of the universe can stay in perfect sync. There'll always be those quantum fluctuations that will cause some regions to contract faster than other regions. So some regions will bounce and reheat before others, and that will lead to variations in temperature across the sky, producing hot spots and cold spots in the cosmic microwave background. And it turns out that it produces a pattern of hot spots and cold spots, which has the same statistical properties as that of inflation, but from a completely different mechanism, not by rapid expansion, but actually by this period of slow contraction plus quantum fluctuations. You can reproduce the exact same pattern of hot spots and cold spots that we've seen in the cosmic microwave background. And we've produced the uniformity and flatness that we were hoping to get from inflation before we discovered the multiverse. So all the properties we wanted have been reproduced in this period of contraction. Another nice property of this is whereas inflation is very unlikely to start beginning from arbitrary initial conditions, because it's very unlikely to have the situation that the field is sitting on top of a plateau at rest in the early universe. A slowly contracting universe begins at very low energies, where it's much more likely to start, much easier to start. More importantly, you don't end up with this eternal inflation. You don't end up with this multiverse problem. Why do we have this multiverse problem in the first place? We had this multiverse problem in the first place because there were these rare fluctuations, these rare procrastinating regions, which quantum physics insisted upon, that kept the universe smoothing, that kept the universe inflating long after other parts of the universe had made their way downhill. In the contracting universe, there'll also be rare procrastinating regions. Those will be regions that will be left behind while other regions who have already finished their contraction, bounced, and expanded. But those rare regions are contracting regions, not expanding regions. Contracting regions do not compete with volume. They never occupy very much volume. They'll just shrink away while most of the universe continues on its way on time, keeping sync with itself. So you don't end up with those rare procrastinating regions taking over the volume of the universe and leading you to the multiverse. So a typical region, a region which reaches the bounds at typical times, will always really remain typical everywhere in space and time.